Good afternoon, everyone. Welcome to another Atom seminar. Today we have the pleasure to welcome Dr. Fufang Yang. He is currently a postdoc researcher at the École Normale Supérieure de Lyon. His research focuses on data analysis and equation of state modeling of thermodynamic properties for aqueous and mixed solvent electrolyte solutions. During his PhD, he worked on various aspects of equation of states for working fluids in energy systems and the impact of working fluids properties and energy system performance. So welcome again, Dr. Yang. We are honored to have you here with us today, and please feel free to start your presentation.
Thank you for the introduction. Thank you for inviting me to this seminar. I'm Fufang Yang. Today I will talk about data analysis and equation state modeling for thermodynamic properties of aqueous and mixed solvent electrolyte solutions. So when we talk about thermodynamic property modeling, we mean some mathematical expression. And we determine these model parameters based on some experimental data. This sounds like just adjusting parameters for some formula, and it doesn't sound very complicated, but it is complicated because there are a few dimensions. There's temperature, pressure, composition, and there are all those properties are related. They are derived from the Helmholtz energy. And then they have to be consistent. We are not developing correlations. We need the engineering models to have some physical meaning. They need to have the correct behavior for extrapolation, for derivatives, for phase equilibrium. And this is not straightforward. Some widely used models today include a cubic equation, shaft type models that I'm going to present about today, and multi-parameter equations as mostly empirical, but they are explicit in the Helmholtz energy. And there are some activity coefficient models, the NRTL, uniquark, they are also widely used. And some of these models are more theoretical, some are completely empirical, most of them are like in between, but some focus more on the accuracy and some try to be as predictive as possible. But when it comes to electrolytes, the models are even more complicated. It is more difficult to use compared to non-electrolyte models that we are more familiar with. And there is a lack of standardization. People define the reference states differently. There are too many units in the experimental literature. I programmed a script to browse the DTU in-house electrolyte data bank, and there were 42 different units for composition. And then there was no critical review or evaluation of the methods. The interactions are more complicated. The ions and solvent molecules are very different, including electrostatic and solvent contributions in the model make the model so complicated that it was not clear how these contributions should balance each other. So the role of and another problem is the role of relative static permittivity. It is also not clear. And there was also no framework for the standard states of solids and mixed solvents. And it is also a bit controversial about the individual ion activity coefficient. And my work was on water, alcohol, halide, mixed solvent electrolyte systems. We only included the methanol and ethanol as the alcohol. There is no application in mind. We worked on this type of mixture because it is the most basic mixed solvent electrolyte mixture. And the goal was to progress on modeling methodology. We want the model to represent the different properties at the same time, mean ionic activity coefficient, vapor-liquid equilibria, and density, and other properties if they're relevant. And we need the model to be to behave properly on both the solvent and salt side. And we need a model to cover large temperature and composition ranges. So to start this, we had to collect experimental data from the literature. We didn't do any measurements, and we had to analyze the data and evaluate the data to have a database, because sometimes the data don't agree with each other. And finally, our goal is to have some generalized conclusion about the equation of state modeling for mixed solvent electrolyte solutions. In the first part, we evaluated experimental data for the mixed solvent electrolyte solutions. We started with the binary mixtures. We used the electrolyte NRTL model to correlate the data. We are using this model because it is widely used model in industry, and it has a relatively small number of adjustable parameters. So it is good for just correlating the data and compare the data with each other. And we removed the data sets are not consistent with the other data. Then we used the binary database for water, alcohol, and water salt, and extended to mixed solvent electrolyte solutions. And in this step, we could focus more on the alcohol salt part. The electrolyte NRTL model is the NRTL model with Peter de Bahakel term and the Born term. We are using a version that is consistent for the composition derivatives, so that it satisfies the Gibbs to Ham equation. The good thing about satisfying the Gibbs to Ham equation is that then the solvent activity coefficient and the ion activity coefficient could be used to verify each other. And because for mixed solvent electrolyte solutions, we don't have a lot of experimental data, it would be good to verify these different properties against each other. And our assumption was that when this Gibbs to Ham equation was satisfied, the model would be more consistent for VLE and mean ionic activity coefficient. These extra derivatives that we included compared to the Aspen model is that is only relevant for mixed solvent electrolyte solutions. When we only have one solvent component, it is exactly the same. These derivatives are zero. And then we compare the results. So we wanted to check if this consistency was really a problem. So we compared the consistent version and the original version of the electrolyte NRTL with different objective functions. In one of the models, we used just the mean ionic activity coefficient as the objective function, and in the other approach, we used both properties. And we find that when both properties are used, this is actually not that important. But when we only use one of the properties, then the prediction for VLE is more accurate with the consistent version of the model. And then we are not really working on model development at this step. We are using this model to compare the experimental data against each other. So for some aqueous solutions, there are a lot of data, and we can be stricter, and data sets are removed to make this scattering smaller. And then we can know that when we actually develop the electrolyte equation of state, the deviation is from the model, it's not from the data. Most of the deviation is from the model, not from the data. And finally, we have this database for the evaluated database for mixed solvent electrolyte alkyl halide solutions, and we categorized the experimental literature into recommended, tentative, and uncertain. And by uncertain, we mean we do not recommend to use it. And this the density is also important for the development of shaft models, but we don't have density from the activity coefficient models. So we used a different approach to evaluate the density data. We just put all the collected density data into a support vector regression model. And this is not to do any prediction. We are just doing this because in thermodynamics, we know how many degrees of freedom there are. So we can use temperature, pressure, and composition as the input variables. And then if the data are of small area, they should just agree with each other and agree with this correlation. And in this way, we removed some data that are wrong and some data that are of higher error uncertainty. And on the bottom are the data that we kept. It is of this scale is much smaller compared to the one on the top, and for all the gray data points are the data set that we removed. Then we have the density database that is needed in the equation of state modeling. And we also developed a MATLAB app in the supplementary material of that paper that people can use to do some quick calculation just for density, accurate density. And then we used this database to develop the electrolyte polar PC shaft. This model includes a hard chain term, a dispersion term, association, polar, and non-additive hard sphere. This is some term developed before in IP, and primitive MSA term for the electrostatic part and bond term for the solvation part. In the primitive MSA, the water is treated as a dielectric continuum, and the relative static permittivity is input in the model. But there have been some literature that proposed that for ion solvent interactions, the electrostatic part and bond part do not account for everything, and we also need short-range ion solvent interactions. In the literature, usually the dispersion approach is used. In this work, we compare if the dispersion association approach, or when using both, would be better. And we also compare the different approaches for the relative static permittivity. We tried two models. One of the model account for the salt composition implicitly. There is no direct dependence on salt composition, but this solution density depends on salt composition. And in the second model, this first model is used, and further salt composition dependence is applied explicitly. Both of these models have weak salt composition dependence. They do not decrease as drastically as the experimental RSP data, but there are some literature that proposed in electrolyte equation of state we should not use the experimental RSP because a part of it is not thermodynamic. And we compared all of these approaches. We regressed the parameters for the 4 chloride salts in a salt-specific approach, just to see how the parameters behave. And we find that when we include this ratio, we can when we adjust the hard sphere diameter, we do not use just the Pauling diameter. We have much more accurate results for density, and then we also find that this ratio is about the same value for the 4 chloride salts. And then but this is not the case for this ratio of the MSA diameter over the hard sphere diameter. And we also find that the 2 RSP models are very similar. And we find that the association approach is more accurate than the dispersion approach. And it is actually about the same accuracy as the full approach. This is really not a fair comparison because we are using different numbers of adjustable parameters here, but we are going to do a fair comparison later. But we also see that this full approach with more adjustable parameters does not make it better. And we used the sum of those conclusions to reduce the number of adjustable parameters, and we also analyzed the sensitivity of the objective function on the parameters to see which to further reduce the number of adjustable parameters. And then we find that then we develop this ion specific parameterization approach. Again, we compare the association approach, dispersion approach, and using both. But this time we have the same number of adjustable parameters. It is not that many anymore. For the 4 salts, we have 15 parameters. And then we could also make it twice, but it will be a little bit less accurate. Here, the comparison shows that the association approach is more accurate than the dispersion approach. And it is actually about the same accuracy as when we use both association and dispersion. And even when we use more adjustable parameters, the association approach is the best. And we also compared the model for the individual ion activity coefficient in sodium chloride and potassium chloride aqueous solutions. The magnitude of the cation or the ion activity, individual ion activity coefficient, opposite. But when we calculate it from the equation state, usually it's just on the same side. So this has not been correctly represented before in the literature. Some papers managed to fit it after including this property with a smaller weight in the objective function. But first, this property is a bit controversial. There are a few papers debating over it. We don't want to get into this debate. And then another problem is that the experimental uncertainty of the individual ion activity coefficient is much higher compared to what we usually use as the VLE and the mean ionic activity coefficient. We do not want to sacrifice some modeling accuracy just to have this relative magnitude correct, but we do want it correct. And we have an ion-specific parameterization approach. So we assume that the ion-specific parameterization approach accounts for the difference of the individual ions by including the different salts with common ions. In this case, it is the anion chloride. And this is, and this worked only for the association, the ion-specific association approach. We can see that here, these lines, this association, the second one is the dashed line is for the ion-specific association approach, and it is reversed. For the other cases, it's all just on the same side. And this is not a coincidence. For some reason, this model does not want to have this opposite trend. When we use the salt-specific regression, the model failed 10 out of 10 times. And then we extended this ion-specific parameterization approach to the other alkali halides. And we had 15 parameters for the 4 chloride salts. And now we could reuse the cation parameters. And when we extend this to the bromides, we have 7 adjustable parameters for the 4 salts. This is a very small number, less than 2 per salt, and it is about the same accuracy. We only had a problem for the lithium salt. When we only used the association approach, we used the anion parameters, or chloride, bromide, and iodide, and the result is not perfect, even at moderate molality. It is not too bad, but it is not as good as we wanted it to be. So we included dispersion also for the lithium ion. This is only for lithium, and for the anions, it's exactly the same. So it's still in the same ion-specific parameterization framework. This is a big table for the for a slide, but if we just focus on the last line, we can see that this model is very accurate. We are using electrolyte shaft, we are using ion-specific parameters, and the accuracy is on the level of 1 to 2%, and even the maximum deviation is quite small. And we also investigated the contributions of different terms in the EPPC shaft in this to the mean ionic activity coefficient, and we see that within the series there are some changes, and this in ion-specific parameters we want some change, and then we can see that for example for the association contribution, it is larger for the heavier ions. Then we extended the model to mixed solvent electrolyte solutions. We started to have some problems. Vapor liquid equilibrium was usually reported for mixed solvent electrolyte solutions at the time. If we are just concerned with VLE, there is no problem. But if we try to model the mean ionic activity coefficient, we see this systematic deviation. And we did try to use the binary interaction parameters, of course, and it doesn't work. It doesn't work whatever binary interaction parameters we try to regress. And we discovered that this problem was actually with the relative static permittivity. It is because this behavior of salts in alcohol and in water is so different that we need to account for this in the model in some way. But we already have those accurate part of the model, very accurate model, and we didn't want to change that part. So when we extended this model to mixed solvent electrolytes, we want to change the model, but only on the alcohol side. So we proposed a few different approaches to change the relative static permittivity model in the equation state. In this approach, this RSP1 represents the original approach, and in this second approach, we use the effective alcohol RSP parameters, and in this third approach, we use the salt composition dependence, but only for the alcohol salt part. And in the fourth approach, we used both. So we tried all of these approaches, and they all work. They all show some improvement for the mean ionic activity coefficient. So this systematic deviation seems to be fixed just by adjusting the composition dependence of the relative static permittivity in the model. And all of these models reduce to the original model when the co-solvent composition is 0. So we don't need to change anything in the aqueous part. And this approach could also be used in some other electrolyte equation of state if they have problem with the mixed solvent electrolyte, but they don't want to redo the entire aqueous parameterization. But when we compare this VLE result between this between the second and the fourth approach, in the second approach we corrected for the alcohol composition, and the fourth approach we correct for both alcohol composition and salt composition, we see some strange behavior here. When we correct for the salt composition dependence, this part is really extrapolation because it already exceeds the salt solubility in pure alcohol. But it is extrapolation, but it is a bit scary because it is a vapor pressure elevation. We don't want this. So if we have to show preference between these approaches, we prefer not to change the salt composition dependence in the RSP. We prefer to keep the keep the implicit salt composition dependence and just change the alcohol composition dependence. And we extended the model to anhydrous solutions for these mixtures. the data situation is much worse compared to the mixed solvent electrolyte. There are usually just 1 or 2 data sets, and most of the time they are contradictory to each other. That is why we didn't use them for the École sort parameters. And we see that the model also agrees qualitatively with these anhydrous binary data. And in the next part, I started to work on ampering in EPPC shaft. After I left, there are still some ongoing works in ILP about ampering in our association. So in this part, we proposed a new association framework. In our association approach, the association sites on the ions bond with solvent molecules forming the solvation cells, also with the counter ions forming the ion pairs, but it is not really ion pairs because there are multiple sites, and it actually forms ion clusters with more than 2 ions. What we want to do here is to label the sites for the cation and ion association. There are just one site. There's just one site, so it doesn't allow for clusters of more than 2 ions. And for the solvation, there are multiple sites. We used the same parameterization approach and the same database. We observed a small improvement compared to our previous result, which is already very accurate. And we see that for this abnormal behavior of the MIAC, this model also managed to predict, because there is a maximum of the meonic activity coefficient of sodium chloride at about 315 Kelvin. And usually when we use the equation of state, it would be more just a monotonic, but we managed to get this curvature in the labeled site approach, this ampering approach. So, and that explains why this model is more accurate than our previous approach. And we also see some change in the number of bonds from the model. We find the ampering approach to follow a chain, but the previous approach presents some more random numbers for the number of bonds. So the conclusion is that we extensively collected and evaluated experimental data for the thermodynamic properties of aqueous and mixed-solvent alkali halide solutions. For the aqueous solutions, we compared different approaches in the EPPC shaft approach framework, and we proposed to use the ion-specific association parameterization approach. For the mixed-solvent alkali halide solutions, we find that to improve the model's accuracy for the mean ionic activity coefficient, we can adjust the relative static permittivity, and we recommend to just adjust for the co-solvent composition dependence. And then we proposed a new association framework to explicitly account for ampering. The work was supported by the ERC, and I would like to thank Jean-Charles, Jojos, and colleagues in IPN. Thank you for your attention.